Talked about how if we opened up every single cell and every single alveoli in a lung, it would stretch across an entire tennis court. That's a surface area to volume ratio. When you fold that back in, all that surface area from the tennis court is getting compressed into this particular volume. Okay, that's a pretty amazing thing. We talked about mathematically how that happens, where if you break things up, like if you take something that had a 2 millimeter radius and then you turn it into something that has 1 millimeter radius, you're going to increase your surface area 4 times the total surface area by just making them into smaller units. We see this all through life. You see that in your digestive system. Remember, we folded those bad boys into your intestine at 23 feet of intestine, and then you folded it into your gut. Not only that, but you had these little like straws sticking out that was helping absorb all that food. So we see that all the time. We see that in our lungs also. All right. And there's our math. Really simple. Here's our surface area to volume ratio is up here around 3.5. To have a higher surface area is a good thing. So I have a higher surface area when my cells are small. This is a test question. This is basically talking about cells are small so that they can increase their surface area to volume ratio. When a cell gets bigger, it has a hard time getting rid of waste and gaining nutrients. Got it? Okay. We talked about alveoli. We talked about the oxygen movement back and forth across the membrane. We talked about here, if you smoke or vape, something's seriously wrong with you. You're not understanding how life works and you're going to put damage into your body. So hopefully some facts on that helps you make a better decision if you're in that category. And then the cell membrane. So the cell membrane, we talked about how you have to have, this is on your test, this picture. I converted it to grayscale. I erased all these parts and you have to memorize all the parts. So you can simply practice by blocking these off and kind of naming what they are. All right, you have a phosphate head, you have the lipid tail, you have a hydrophilic phosphate head here, hydrophilic phosphate head here, and then the whole middle, like it says here, is your hydrophobic tails, which means it hates water. Then you have a series of different type of proteins, and I think we talked about all those different proteins, how some are a channel and allows things to go through, allowing glucose to go through. Carrier proteins grab it on one side and they kind of flip it to the other side of the membrane. Recognition proteins are basically to identify you and who you are, so your body can identify what's foreign and what's you. And receptor proteins basically are receiving different messages. Insulin receptors, human growth hormone receptors, adrenaline receptors, and then you have your enzymatic, which break things down and build things up. So I think we did a good job there. Talked about some examples with different tribes and how they have a genetic difference that allows them to have fewer or more human growth hormone receptors. And then this is a really, really, really important slide. I'm sure you've started 5 times over. We talk about that we have small and or uncharged particles that can move freely through a membrane. Then we have large molecules that need a carrier or need a channel. We talked about ions or positive and negative charges that also need a channel. And our example given was the chloride channel with cystic fibrosis. And I know we got to this slide, right? We got to this slide. Okay, what I'm looking at here with this slide, I want you to just take a minute and read the diffusion one again. Just read it and really absorb each word, and we're going to talk about that. So just take a minute and just read it on your own. What words in that are confusing? Because this is a very complex, thorough definition. You know what net means? Okay, net. All right, you ready? If I'm a kid and I have a lemonade stand and I have to buy cups and lemonade, and it costs me $2. Okay. And then I sit out on the corner and I'm selling my lemonade and everything's great. Bingo comes by, buys a cup, all that kind of stuff. And the total money that I made was $4. My net profit would be $2. It cost me $2 to get going. I got 4, so I kind of do a little subtraction and I get 2. So net movement means that there's going to be some positive and negatives, but in the overall end, what are your total positives? Okay, and we're going to look at that with a picture in a second. And then do you understand what random means? The way I tried to get you to understand random was putting little motors inside those ping pong balls and letting them bounce everywhere. You have no idea where this thing is going to go. Those of you that played baseball or softball, remember those reaction balls where they're a little oddly shaped and you throw them and they bounce and you cannot predict where they're going to go? That's a random movement. Okay. So it's a net random movement, high to low. So let's look at that. Yeah. Okay. So let's look at this guy. So here's our diffusion. I know we went over this, but I just want to do it a little bit more. So let's say each one of these is an oxygen molecule right here. I kind of colored it red. What net means is that some of those molecules, believe it or not, will go back this way. Okay, but I'm going to get a lot more going this way. And the reason I'm going to get a lot more is because these molecules here are tighter and closer together. So these are constantly moving and bumping into each other. So if they're moving and bumping into each other, it just sends them all over the place. And then they're naturally going to move to the other side. Now, when these on this side of the membrane, on the inside part of the membrane, they're also going to bounce and move, but they're a lot more spaced out. So the likelihood of them moving across the membrane is lessened. Okay, so here's net. I have 1, 2, 3, 4, 5 arrows going one way, and I have 2 going the other. So I'd have a net movement of 3 molecules on this side. Does that make sense? And then the randomness happens because we don't know which way this ball is going to bounce or this oxygen molecule is going to bounce. We just have no idea. Okay, so net random movement. Here's my high concentration. Here's my low concentration. So it's always from a net random from a high to low. Shake your head and smile awkwardly if you understand that. Good, Alex, you do very good with the awkward. All right, so now sometimes, like in this case, these molecules can't move across the membrane. And the reason they can't do it, well, let me ask you, why can't some of those molecules move across? It was in a previous slide. Alyssa, tell us why some of those molecules can't move to the other side. There's 2 reasons it could be. Any idea, Alyssa? Draper, how about you? Are these people trying to talk? Am I missing something? Bella, are they trying to talk? You guys are making this so hard. Somebody say something so I know your volume actually works.
I can hear you.
Carter, what's going on here, man? How come no one's talking to me?
No one's answering.
I'm feeling really lonely out here. No, I'm serious. It's a little depressing. I'm going to get another cup of coffee. So, Carter, since you can hear me, the reasons why these move across is because they're small and uncharged. Why can't these move across, these big green guys? What do you think?
Because they can't fit in between the I forgot what that layer's called.
The phospholipid bilayer? Yep.
Or if they're charged.
Good. So they're too big. Too big or they're charged and they can't move. So what happens is they get help with the protein. They'll literally go in this protein, it'll squeeze them out the other side, and they call that carrier-mediated facilitated diffusion. This guy, these might have a negative charge to them. So yes, there's a higher concentration, there's lower here, and they move, but they need the help of this protein channel because there's charge and they just get repelled off the membrane, the selectively permeable membrane. Okay? All right. This is going to be the hardest slide we do probably all year. So take a deep breath. Is everybody taking a deep breath? Bella, I can't see. Ashley, are they taking a deep breath?
Sure.
Oh, finally. Finally. All right. Here we go. So we have to be very careful with this. This is on your test in a similar form, not this exact picture. There's no way you can cheat on this because it's all thinking. It's all thinking. Okay, so here we go. If I were you, I would draw something similar to this really quick. I mean, this one's tough, and it's about 5 questions, and we got to get it right. And we're going to do a lab on it, so you're going to have to explain it with a lab. Okay, here we go. Should I give you a minute, Carson, should I give you a minute to write, you think? Yeah? Okay, you have 1 minute to write.
Ladies and defaults, we did it. The final day of seaweed. I'm gonna keep it real
Hey,
with you guys
bingo.
right now. I almost folded about
What are you
27
listening
times
to
this
today?
week. It's been a long
right now,
week.
I just
Now,
got some
before I
Christmas
pass out, I
music
want to let
on.
you guys know what's
Really?
going on in this video.
You know what? What's your favorite
Look at him.
song in a movie?
Hold up.
Any movie?
Yeah,
This
any movie. What's your favorite song?
Except Andy's dancing.
This is officially my first playground video. Today's video is just a compilation of random dumb
I don't
stuff
know.
that's happened in
You wanna know
playground.
my
By the
favorite?
way, I'm not
Which
going in
one's
SC
what?
today. I'm using another.
I like
And lastly, I
Do
don't
You
talk
Know
about in
the
this video
Muffin
because
Man
pretty much every
during
time I
that
do,
Shrek movie?
this happens.
You sound like
Isn't that
someone
good?
I know. Like you sound like C-Day.
Why does this guy sounds like
Just
C-Day?
checking in, making good.
C question mark.
Why does this alligator
Emerson, how about you? What's your favorite
sound like
movie
C-Day?
song?
C-Day. Ladies and gentlemen.
I knew it! Yeah. No one wants to
Who
get
want
up
to be on
there.
my team? Does anyone of you want to be?
All right, Carson, has that been a minute? Can I go now? Okay. If I ask you a question, who should I pick on? Let's pick on, let's make it dramatic. Let's find someone really shy. Let's go. Let's see here. Who should I pick on? You know, okay. All right. Let's go with Hadley. Hadley, I'm gonna go over this, and if you can't get it right, you have to sing Do You Know the Muffin Man? Okay? So pay really close attention. And if she gets it wrong, I'm going to move to the next person over on my screen. So whoever's right next to her on the screen at that moment has to go to the left. You hear that, Emily? Okay, here we go. When we're looking at these, this is what's crazy important. These green guys are, let's call them a salt. Okay. And the reason I want to make sure we understand that a salt's going to have a charge to it. That means that the green cannot go through the membrane. So this red line is a selectively permeable membrane. So the water molecules can freely move back and forth. Water, the blue, can move freely back and forth. But the green solute, which is something dissolved in the liquid, and we're going to call it salt, cannot move across it. Can never do it. Okay, so that means the fusion will not happen. But if it's the movement of water from a high concentration to low, that term is a special term called osmosis. So we're dealing with osmosis right now. Hear that, Hadley? We're dealing with osmosis. All right, so now, if I go in this green guy right here, this green container, so it's 10% salt, which means, and whenever I have a problem like this, I would write on the test the 90% water. So that means that this is 5% salt. So what percent water would that be? Anybody? You don't have to sing. You know the Muffin Man if you get it wrong. What percent?
5%.
How much?
5%.
It's 5% salt, but how much water then is it?
95%.
95%. Okay. So I can't deal with high-low concentration of salt. I can't do it because the salt won't move. But I can deal with high-low concentration of water. Okay. And in this case, this is a 95%, which is a higher concentration than 90%. So that tells us that water would move from here into this, right? It's going to move across the membrane. Now, if we look here, and I'm just going to count arrows that are going into it. I have 1, 2, 3, 4, 5, 6 arrows going up, and I have 1, 2, 3 arrows going down. So that's kind of our idea that there is random movement. We're going both ways. And it also shows us that there's a net gain of 3 going up, right? So that means the water's moving up. So this is a before, and this guy's after. So this is like after, like, let's just say 1 minute. Okay. So now they kind of trick you with you. They're like, okay, this is actually greater than 5% water, and this one's actually less than 10% water, right? So this very well could be like 93 and 93%. Okay, and maybe this is 7 salt and this one's 7 salt. That 7 would be greater than 5, 7 would be less than 10. So that tells us that water moved in here. And it's evidence because you could see that it rose, you could see the level rise there. Okay, so the water moved in. What's really, really, really hard about your test is the questions I'll ask you. So if I gave you this situation and I got rid of the numbers, you would have to predict what would happen there. So for example, right away, I have evidence that it moved, which means I have evidence that water moved in. And and here's the hard question, and it's not you, Hadley, yet. I'm saving a real hard one for you. You could say that if I looked here and I could say, what do you predict the percent water right here? What would you predict it to be? Not knowing anything I just told you. And I could give you answers. I'd give you answers like 93, 90, or 85. And obviously we know 93 would be the right answer, but it's the idea that the water moved back and forth, so it lost a little water. So it went from 95 to 93. Okay, in concentration. Then I can ask you what the percent water could be in here. And you would have to tell me, and if I give you multiple choice, 90, 93, 85, then 93 would be the right answer because, again, the idea that it's moving in and becoming more dilute. Okay, here's the really, really hard question. Think about this. Even though the key here is, even though the percent has changed, does the amount of solutes in this ever change? Not you, Hadley, not yet. No, you thought you got that one right. The amount of solutes, does it ever change?
No,
No.
because solutes can't go through the membrane.
Right, and you're going to get tripped up on that. There's a difference between amount of solutes and percent of solutes. Just be very careful with that. Okay, we'll come back to this one more time. Hadley, here's your question. Are you ready? Do you know the Muffin Man? Do you know the song?
Yeah.
Okay, good. So I'm ready. The question is, what process did we demonstrate with water moving across a membrane?
Osmosis.
You got it right. That wasn't hard enough. Should I give her another one? Or should we move on to Emily? Oh, I just see her eyes get big. All right, we're going to go to the next slide. Good job. So here's going to be our lab. So let's pretend that we have a cell here. Okay, and now you're looking at amounts, and amounts is fine, but we have to deal with concentration. So in this case, I have a cell in a solution with salt in it. Okay, we're just going to use salt or solids, whatever you want to call it. Okay. Isotonic. Iso means the same. Okay, and it's the same amount of particles in this as in the solution. And I don't like, let's change this word. I don't like this. This should be percent. So change that. And here, that should be percent. And here, that should be percent. I don't like the way this slide was written. I don't know if I did that or somebody else. Okay, so isotonic is the same percent of particles in the cell as the solution. So here I have a cell. Let's say that this is 8%. And this solution is 8%. So whenever they talk about isotonic, hypertonic, hypotonic, they are talking about the solution that the cell is in. They're not talking about the cell. They're talking about the solution. So this would be an isotonic solution. So this is going to be A. And what that means is that there's 8% salt solution outside the cell and 8% in. And if you notice the arrows are the same size going into it as they are going out of it, which means water is net randomly moving in at the same speed that net random water is moving out. Okay, now I have a situation, and this is B, this is called hyper. When you think hyper, you're thinking extra energy and extra solids. So here I have more solution on the outside. So let's say this is a 15% salt solution, and inside here is still 8, right? And the thinking would be that 15 and 8, that the 15% solute would go in to the cell, but we know that can't be true because it'll tell you clearly on the test that the salt can't move across the membrane. So if that's the case, we have to do our math in our head and say, okay, well, then that's 85% water, and this one's 92% water. So it's going to go from a higher concentration to a low. So it's literally going to leave in high amounts, and a little bit's going to go in, but high amounts are going to go out, and the cell is going to shrink. Okay, the cell is literally going to shrink when we do that. Okay, in hypotonic, now we have very dilute amounts. So let's say we have 8% here, let's say we have 1% in the actual solution, which means we have 99% water, and here we have 92% water. So the water is going to race in. You can see it's racing in higher amounts, and it's leaving in smaller amounts because it's net and random. And that cell is either going to swell huge or that cell is going to explode. One of those two things. Okay. So if I give you a test question, here comes a hint. If I give you a test question, who have I picked on today? Angel. If I gave you a test question that basically said, what will a cell that's put in a hypertonic solution do? Will it shrink or will it swell? Hypertonic. What will the cell do?
It would shrink.
Good. If I said, Ashley, if I said, what would a cell do if I put it in a hypotonic solution? What would you tell me? So like C, what would the cell do?
The cell will get larger.
Good. And that's what we see here. On top here are animal cells, on the bottom are plant cells. But in hypotonic solution, more water races in and they swell, and sometimes they lyse or explode. In an isotonic solution, water's going in the same speed as it's going out. So if you've ever been in the hospital and put on an IV, they drip sodium solution. I mean, if you ever just read the bag, it'll say sodium solution or salt solution. And what they're trying to do is they're trying to pump liquids into your body, but those liquids have to be isotonic. Because if they pumped in pure water into your body, not drinking it, but pumped it into your body, your cells would explode. If they gave you a super high sugar or very high salt solution, then your cells are all going to shrink. And those are very bad things. That's dehydration. So isotonic is what they usually put in. And you read the bag, and it'll tell you the exact amounts, like 7.8% saline solution. Okay. So here we have a cell being normal, and here we have being true. All right. We're not going to do the math yet. We're going to come back and do a little math on this. Any questions? It's super hard. If I were you, this is what I would do. If I listened to my little lecture on getting a better grade, this is what I would do. I would take today, find some extra time, and I would go through my notes. And I would do one of three things. I would either take all of my notes and rewrite them as an outline, like Roman numeral 1, passive transport. A, diffusion, put all the details in there. B, facilitate diffusion, put all the details in there. C, osmosis, put all the details in there. And just go through and you have to figure out a way to rethink the material, not just rewrite it, but rethink and reorganize it and allow it to kind of sift into your brain so you remember it. You can do that, or you can go back through your notes and just highlight certain parts and then make a little summary box. So you go, okay, this is when he said this, 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 and this. Summary boxes. Summary boxes are really, really, really helpful. Okay. And the third thing you can do is go back through your notes and color code things. So whenever you see it, maybe you make green passive transport. So wherever you see something that had to do with passive transport, you just kind of shade it in green. So you're kind of thinking about it. Okay. Whatever fits your scheme. Okay. But you got to rewrite these notes. These are tough notes. Okay. If you wait for the weekend and then all of a sudden next week we take the test, you're like, oh, I didn't know we had that on the test. That's a bad thing. All right, real quick, everybody open up your assignment. We're going to color. I'll show you how we're going to do it. It's going to be super fun. Can't wait. Luke, look excited. So when you open up the PowerPoint, I should have made it so you can write on it or edit it. So what you have to do, and if I'm going too fast, catch up. What you have to do is open it up into the full presentation mode. You will not have these tools if you do not open it up into full presentation mode. Okay, so it takes up the whole screen almost. Okay, and you should still see our faces kind of